So for this video, we're going to be going over sections 3.3, infinity, along with sections 3.4, trig limits. All right. So to start off, what we're going to be doing here is we're going to go over infinity. Essentially, what we're doing when we're trying to figure out infinity is we're taking limits, right? A limit as x approaches some certain set of value, right? So I'll just say here, to find what the function approaches, you take the limit as x approaches negative or positive infinity. Okay, so for our first examples of this, here, let's say example set one, right? As a really easy limit, we're gonna set it up as the limit as x approaches infinity of 2x plus 1. So when we see something like this, we're trying to figure out what happens as x gets really, really big, right? So if we look into our function here, 2x plus 1, x gets really, really big, right? This one term here really isn't going to matter, right? And then whatever value of x we're having, we're multiplying it by 2, right? So you can kind of see here that x gets bigger and bigger and bigger. The value of our function is also going to get bigger and bigger and bigger. You can see here the limit is going to be infinity, right? And then you can see here, if we do another problem, the limit as x approaches infinity, or x squared minus 5. We're also going to have a similar case. Our negative 5 is pretty much going to become non-existent as x reaches infinity with these bigger and bigger values. Along with whatever x value we plug in here, it's going to end up getting squared and multiplied by 4, making it even bigger. So going to end up with infinity, right? And then another way to see it here, x approaches, say, negative infinity. Go with the same original function, 2x plus 1, right? Our one term really doesn't matter here again. And we're plugging in a negative number into this 2x, right? Now, if we plug that in, you could see we're just going to get bigger and bigger negative numbers. So we're going to approach negative infinity, right? And then say we take another limit, the limit as x approaches oh, infinity, squared minus 3, right? Some may think this would approach negative infinity, but if you look at our term here, we're approaching negative infinity, but this is a squared term here. So whatever negative number we try to plug into it, we're always going to get a positive number. And remember, since this negative 3 is just a constant term, it's not going to affect when x approaches these really, really big or really, really small numbers. So in this case, it blooms out to infinity. Now, those are the easy versions of limits. Then the next, I'll say here, set 2. Let's say we have the limit as x approaches infinity of this function x plus 2 over 2x, right? When you have something like this, we have to remember roughly what we were talking about before. When you have these really big numbers that you're getting to, right, your constant terms really don't matter. You can kind of just plug those out. So we're able to say when x is approaching these really, really big values or really, really small numbers, that constant term 2 doesn't exist. So we can just make it x over 2x, right? Which then can further be simplified. Hold on here. Let me move this down. We can then say that this is now equal to 1 over 2 if we just take out of x, right? So as our function, right, x over 2 divided by 2x with the limit as x approaches infinity for this, it's going to approach 1/2 as a value. And then if we do another problem, for example, here, say we do the exact same problem, right? The limit as x approaches this, but let's make it negative infinity, right? Let's do the exact same problem and let's see if there's a difference. So if we run through the same steps that we just did here, we plugged out the 2, we got x over 2x, we took out an x, we got 1/2. See, look, it doesn't matter if we put in negative infinity or positive infinity, we're still going to approach 1/2. You can kind of see this if you think about it mathematically a little bit. If we plug in a negative number on our top here and a negative number on our bottom here, right? A negative divided by a negative, you're still always going to get a positive number. So that's where that whole cancellation comes from, and you're still getting the same value. Now, see another good problem here. Let's go with the limit as x approaches infinity of, let's say, the function. What would be a good one? Let's go with x squared minus 3x plus 2 over, let me move this over a little bit further, over x squared minus 3x minus 4, right? So similarly with how we did before, with our, as x approaches these bigger and bigger values, some of these terms don't matter. When you end up with functions like this where you have different degrees, what you do is you only focus on the highest degree. And so in this case, our highest degree is 2 with our x squared functions on the not fun, x squared degrees on the top and bottom. So you end up getting, when you get rid of your lower ones, you just get x squared over x squared, right? So what do you end up with? You just end up with 1. So the limit as this function x squared minus 3x plus 2 divided by x squared minus 3x minus 4, that limit as that approaches infinity is just going to be 1, right? Now, if we take a different function, say limit as x just approaches infinity, let's give a similar problem, but let's just change some things around. Let's change the coefficient here. Let's say this is 2x squared minus 3x plus 2 over x squared minus 3x minus 4. When it comes down to a function like this, it still comes down to the degrees of the function. Those are the highest degree parts of the function you want to be analyzing here, right? So it'll be our 2x squared over x squared. But now the biggest difference here is you can kind of see you can cancel out those x squareds, right? So then it comes down to how big is the coefficient, right? In this case, the highest was the coefficient of 2. So once you cancel out these x squareds here and here, you just end up with 2, right? Now, that goes over that. Here's another example of what could happen. Say the limit as x approaches infinity of, let's go with 2x cubed minus 3x plus 2. Bend this out a little further. Over x squared minus 3x plus 2, right? What you get here is we still look at our highest degree, right? And we get 2x cubed over x squared, right? And so now, like what we did before, we can see we can get rid of a x squared off the top and bottom. And then we're going to end up with 2x over 1, which is then equal to, here, I can actually just move this over here, which is equal to 2x, right? And so then we can say the limit as x approaches infinity of 2x, right? We kind of saw that before with the previous problem, right? When we plug in these values for x and they get really, really big, it's just getting multiplied by 2. So it's also just getting really, really big. So we get that the limit of that whole function, 2x cubed minus 3x plus 2 divided by x squared minus 3x plus 2 is going to approach infinity. Then there's a couple other important things to know when taking limits. We'll get into when it comes to exponential functions. Let's see here. So exponential rules. So what you need to know is, hold on, let me fix this here. There you go. When you take the limit as x approaches infinity of e to the x, you're going to get infinity, right? And then when you take the limit as x approaches infinity of e to the negative x, you get 0. And then the limit as x is, approaches negative infinity of e to the negative x, you're going to get negative. You're going to get infinity. Then if you take the limit here, the limit as x approaches negative infinity, negative infinity of e to the x, you're going to get 0. Now, with this, we can bring this together and then see what we can do here. So the first problem that we can start doing with this, say, example set, the second, right? No, 3. We can then say we want to evaluate the limit as x approaches infinity of, let's see what I do. 1 over 1 plus e to the x, right? Now, actually, you know what? Let's make it 1 over e to the negative x. So, with this one here, we need to see, let's figure out our terms here. When x approaches infinity of 1 over 1 plus e to the x, right? If we look back at what we have here, we know that the limit as x approaches infinity of e to the negative x is 0, right? So we must be able to say that this must be equivalent as 1 over 1 plus 0, which then gives us 1 over 1. So it's just 1. So we're able to say the limit as x approaches infinity of 1 over 1 plus e to the negative x is just 1, right? Pretty simple. And then we try another one here. Try to figure out the limit as x approaches infinity of e to the x plus 1, right this here, e to the x plus 1 over e to the x minus 1. So if we look at this here, this is similar to like what we did with our previous problems I talked about. When you get these really, really big values, these constant terms you can really just plug out because they don't affect anything. So you end up with e to the x over e to the x, which since these are the same thing, you just end up with 1. Pretty simple, pretty straightforward. Now we'll get into trig limits. Now, for trig limits, what we're going to be going over is essentially first the bounds for our sine and cosine function, right? Well, we know that the bound for cosine of x is going to be -1 over cosine x, not over cosine x, -1, it's going to be greater than or equal to that, and then from here, it's going to be less than or equal to 1, right? And then for our bounds of sine, it's going to be the exact same values. Sine x, right? And then another thing that we're going to need to know is that the limit as x approaches 0 of sine x over x is going to be equal to 1, and that the limit as x approaches 0 of 1 minus cosine x over x is going to be equal to 0. Right. So first, let's break out what these bounds mean. So essentially, let's work this out graphically, make this easier to see. For a cosine function, right? Let's say this value here is 1. Let's say this value here is -1. Remember that the cosine function and the sine function are just oscillating wave functions, right? So they're just going to go back and forth, reaching max peaks of 1 and -1, just as the cosine and sine function. That doesn't include if it gets multiplied, divided by, or modified in any other way like that. Then your bounds could end up being different. But the base function is like this, right? So that means that we're able to put these restrictions on where we know the values of sine and cosine are going to be. They're going to be somewhere around there, right? And so what we want to know here is we want to be able to evaluate some functions, right, as they approach this value of infinity, right? Because you can't directly plug in infinity into these trig functions, right? You can't just plug it in and get a value. Like with normally, you could plug in like, oh, 90 degrees or pi over 2, and you could get a value, right? So this is where we get the sandwich theorem or the squeeze theorem. Okay. So basically what the squeeze theorem says is, say you have this function f of x, and it's e to the negative x cosine x, right? And you want to evaluate this limit as x approaches infinity of e to the negative x cosine of x, right? You want to evaluate that, but you can't plug in infinity and see what happens. You could try plug it in, and you could get something out for e to the negative x, right? But then what happens with cosine? So what the squeeze theorem says is, if we have this function here, and we know that the bounds for cosine for this one is -1 to 1, we're able to use what we know here and then multiply in what we don't have. So we see that we have a e to the negative x that's there that doesn't pop up in our bounds. So what we're able to do is put -1, and then let's just rewrite e to the x, e to the negative x to 1 over e to the x. And then we can multiply that by -1, keep our same bounds here, put in the function now that we're trying to evaluate for, which is e to the negative x cosine x, and then multiply this one by 1, which is still going to give us our same function, right? And then now we can begin the process, and let's say we evaluate the limit as x approaches the limit, as x approaches infinity, my bad, of each individual function here. And that is the magic of squeeze theorem, because now we're able to do this. We have X, limit here. Now, let's start evaluating the limits. So, we know that the limit as x approaches infinity of e to the x is just 0, right? So, and then 1 divided by 0, right? We, and then it doesn't matter the negative number there. We know that this limit is going to approach 0, right? Goes here, right? And then if we go and look at our right limit here, we know that same as before, as e to the x approaches infinity is 0, 1 over 0, we're going to get 0. And so just rewrite it here, this. So we know that this is going to equal 0. So now if we go to look back at what we have here, we know that our limit as x approaches infinity of e to the negative x cosine x is going to lie somewhere between 0 and 0. But if you think about it, if it lies between 0 and 0, there's no number in between those. So that must mean that the limit as x approaches infinity of e to the negative x cosine of x must also be 0. Because there's no other numbers between 0 and 0, right? So then if you want to put that into a sentence, you could say, I squeeze theorem, squeeze theorem since the left and right limit both approach the same number and the function of x lies in between this f of x must also have the same limit. And boom. With that, that goes over all of squeeze theorem. And all you need to know with that is that you just take your base function that you see, right? And then whatever extra added terms that you may see, in this case, ours was e to the negative x. All you have to do is just multiply that into your negative one and one bounds, and then evaluate your left limit, your right limit, and if they both agree to the same value, right, and there's nothing else in between them, like we got here, you're able to say, well, boom, that must mean that our inner limit is also the same, right? So that was the bulky part there. Now we can get into evaluating our other limits, our other trig limits. Move down here. Segueing off that, we'll go with the limit as x approaches 0 of the function sine x over 1 minus cosine x. So a little further. Over, let's say x squared, right? So as you can tell here, it kind of looks familiar from the two uh, limits I gave you here, right? The answers to those. So what we can do here is actually just break this whole function down. We can then say that this is also equal to sine x over x multiplied by 1 minus cosine over x, right? Because if you just multiply those two functions together, you end up getting our same function that we started off with, right? So then we can evaluate those individually and then determine what our limit of that original function is. So if we look back here, we remember that our limit as sine x over x approaches sine x over x approaches 1. and then our limit is 1 minus cosine x over x approaches 0, we can then say this just turns into 1 multiplied by 0, which, we know then is 0, right? And then our next one we can go over is the limit as x approaches 0 of sine squared x over x, right? Now, this kind of looks familiar here, right? But what we can do is, remember, we want this to look like sine x over x, right? All this is missing is this one isn't multiplied by x, right? So the idea here is if we multiply this by x over x, we can then say, make this sine x squared over x squared, right? But then all we did was just kept out an x, right? So we multiplied this one across and we get the x squared. But this one, we just kept out to the side, this top x. Because then this sine x squared over x squared, that's equivalent to sine x over x. Those are the same things. They both have the same degree. So then, oh, we can just evaluate each one of these individually, right? And remember that sine x over x, what does that equal? That's going to be equal to 1 as it approaches infinity. And as x approaches, I mean, not infinity, as x approaches 0, and we remember that the limit as x approaches 0 for x, well, you can kind of see that's just 0, right? You end up with the whole limit being 0, right? Now, the next thing you can get into, kind of a similar one like that. Let's say we take the limit as x approaches 0 of sine 3x over 2x. Remember, we want it to look like sine x over x, right? Or an equivalent form of that, right? So what we can do here is multiply this by 3 over 3, right? And then when we do that, we can now rewrite this 0. We want this to look like sine 3x over 3x, right? And then we can just pull out the rest of that 3 over 2, right? And then if you actually look, if we multiply this across and this across, you still end up with the same thing as if we did this, meaning that we didn't change the function at all, but we're still able to now evaluate this limit, all right? Because you multiply, you get 9 here, you get 6 here. We do this, you get 9 here, you get 6 here, which means we're good. And we know that since these are the same to like the same coefficient here, we can evaluate that limit there like normally, right? You go check back. We say, oh, what's this limit here? That one, it approaches 1. And then this is just a constant term, so it doesn't matter what x approaches. So what we can do here is just say this just turns into 1 multiplied by 3 over 2, which means our entire limit here is 3 over 2. Now, an easy little trick that I like to do when it only differs by the coefficient is your answer is literally just this. If you see a 3 at the top, 2 at the bottom, your answer is just going to be 3 over 2. So a good way to check now is if you already know that your answer is going to be 3 over 2, and all you need to do is just check, well, not check, you need to go over the steps of your work. You already know the answer, so just reverse engineer the answer from the problem, right? So that's pretty much all you need to do there. And then for our last problem, we're going to go over the limit as x approaches 0 of sine x squared. Actually, no, I got a better idea. Let's go over the limit of 1 minus cosine squared 3x over 9x squared, right? And so this one, it looks a little bit more tricky, right? You don't know where to start. We know we see some things that kind of look familiar here, right? We see the 1 minus cosine squared. right? But we know that we really need to be in 1 minus cosine. We don't know where it is. This is where we bring in our Pythagorean identities, right? So if we come here and we remember that, here, if we remember that sine squared x plus cosine squared x is equal to 1, we're able to now bring this over. We hook this right here. We can we can now rewrite this as 1 minus cosine squared x is going to be equal to sine squared x, right? You see, if we just move over our cosine squared over to the other side, subtract it over, right? And that looks eerily familiar to what we have here, right? Except for that 3x. But we're still able to replace this in. Rewrite this. It's kind of bad. So we're now able to rewrite this function as sine squared 3x over, and if we see this again, what we notice here is that this is actually just a squaring of 3, right? So then, doesn't this look really familiar? It kind of looks like it has the same coefficient, and they're both squared, right? So the next step that you're able to take here is, let me move this up so I have a little bit of, ooh, move this up so I have a little bit of space. The next step that you're able to take here is to then say, this is now equivalent to sine 3x over 3x, but the whole thing squared. But now we're able to evaluate this limit because we know what this limit of sine 3x over 3x is. We know that this is just 1. And since this is just that whole function squared, it's just 1 squared, which is then 1, right? So this is the whole solution for what that limit of it is. And with that, that goes over everything that we need to know for 3.3 when you have limits approaching infinity, and 3.4 when you're figuring out trigonometry limits, right? And so, as a brief overview of what you need to remember, when you have a limit of a function, right, and you're approaching these really big values, you always want to look the highest degree part of the function because lesser parts, like lesser degree parts of the function, won't really matter as you reach these really, really big numbers or really, really small numbers, right? And then we also learn techniques where once we were able to get rid of those coefficients or lesser degree parts, we were able to just uh, subtract away the lesser parts and end up with actual values for these limits, as we saw here with x plus 2 over 2x, where we were able to get 1/2, or this one, x squared minus 3x plus 2 divided by x squared minus 3x minus 4, right? We were able to get 1, and then the other question right next to it, 2 respectively, right? And then we also saw when you have an even higher degree function on the top, right? Like where we saw where we had x cubed on the top, and the part on the bottom was a lower degree that it bloomed out to infinity. And we also know similarly, if we have a function where it's an even higher degree on the bottom and a lower degree on the top, that it's just going to approach 0. And then we went over our exponential rules here, where we know that our limit as x approaches infinity of e to the x is infinity, limit as x approaches infinity of e to the negative x is 0, limit as x approaches negative infinity of negative e to the x infinity, and then the limit as x approaches negative infinity of e to the x is going to be 0. And we know those, and you can kind of visualize it if you see the function of e to the x itself and negative e to the x respectively, and just kind of see where it's going when you plug in these bigger values of x or smaller values of x. You can see what's happening there. And then we also went over our bounds for the base functions of cosine and sine being -1 and 1, and about it being an oscillating function where its value is always going to be somewhere in between those. And we were able to use that and apply it to evaluate more complex limits that we weren't able to do normally using the squeeze theorem. And then we also remembered and went over our limits for the limit as x approaches 0, sine x over x, which we got 1, and then the limit as x approaches 0 of 1 minus cosine x,